Hey everyone, my name's Cortney Dieterle and I'm here with
Jenni Sinan
and Ashley Russell.
And today we're going to be talking to you guys about our 370 project.
From our research, we were able to find that the peanut M&M manufacturing process is as follows. First, the chocolate is made and poured over the peanuts in silicone molds. Once the chocolate is hardened, it is then tumbled until they are made smooth. Next, the candy coating is sprayed on in layers and proceeds to have the M stamped on. The factors we found to be critical to quality are the size and shape, the ratio of colors in a bag, the total number of M&Ms in the bag, and the stamped on M. We bought two 2-pound bags of peanut M&Ms, counted all of the defects in both bags, and then took random samples from each bag and counted the defects. We were then able to do statistical analysis of the defects. Based on the analysis, our goal was to find ways to improve the process of making the peanut M&Ms. In order to account for M&Ms that have more than one defect, we assigned priority to the defects. Stuck together M&Ms take the highest priority, then chipped M&Ms and deformed M&Ms, and lastly, an incorrectly stamped M. In the center is what we consider to be the perfect M&M. On the top was our stuck together M&Ms. On the right was the no M or a messed up M. The bottom is what we consider to be a deformed M&M, and on the side is a chipped M&M.
So here's a concept map showing the M&M making process. We have our controllable inputs or our factors at the top. It consists of the chocolate supplier, time being tumbled, and the time between the coats getting sprayed on. On the bottom is the uncontrollable inputs, things such as humidity, ambient temperature, and human error. And then the outputs are the actual M&Ms that are produced and the number of defects that come out. So for this project, the primary tools used for analysis were charts, inspections, and experiments. The tools for process improvement was primarily a DOE. Data to be collected and analyzed was the total number of defects found in two 2-pound bags of peanut M&Ms, and using a theoretical DOE, could this number be reduced? So here just shows a little bit of the data that was collected. In bag 1, we found that 25% of the M&Ms were found defective. 17% of these defects were from the stamped on M being messed up. In bag 2, 31% were found defective and 15% had defective M stamped on them. After we collected this data by sampling the entire bag, we did 3 random samples from each bag, and the graph to the right shows the overall number of defects drawn in each sample.
So now we're going to talk a little bit about the charts that we made to analyze the data. So this first chart on the left is the P chart, and it shows the proportion of defects per bag per sample. So the first 3 data points are from the first bag, and then the next 3 are from the second bag. On the right, we have the mosaic plot, which compares the type of defect per color of M&M. So you can pause it and take a look at it if you want, but basically it just shows how many different defects per color of M&M there were. So here we have our contingency table, and this is it's a lot of numbers, but I'll just go through how you would interpret this chart from just the first block. So right next to blue and right underneath chipped is where I'll be going through. So the 5 is the count of blue chipped M&Ms, and that's just how many chipped M&Ms were blue out of the total chipped M&Ms. And then the second number is means that the blue chipped M&Ms are 1.16% the total defects in the bag. The next number below that, the third, means that the blue M&Ms make up 15.15% of all the chipped M&Ms in the bag. And then finally, the fourth number means that the chipped M&Ms make up 9.8% of defects among blue M&Ms. So you have those 4 numbers for every combination of defect and color, and then their totals and their percentages along the edges of the table. On this slide, we'll talk about the ANOVA test that we ran for the project. So this test was meant to see if the average number of defects varied by bag. So when we ran the test, we got a p-value of 0.1216, which tells us that the means are different. So there is a difference between number of defects between bags. And that lets us know that there's unwanted variation in our process. And this is one of the major areas for improvement that we found among the process. So there are a lot of defects, and then it's not a consistent amount of defects in each bag. So these defects are coming from different areas in the process.
The graph on the left shows the overall number of defects found in bag 1, broken down by color. And as you can see, the orange line represents a cumulative percent of defects for the whole bag. After we found the total number of M&Ms per color and the total number of defects per color, we were then able to calculate and show the percent of the specific color that are defective, which is represented by the gray line in the graph on the right. The box to the left in each color represents the total count of defects per color, while the box on the right represents the total M&Ms per color.
So here we have our theoretical design of experiments. So the table on the left shows how we chose to set up our experiment. So we had 2 possible chocolate suppliers and 2 possible peanut suppliers. We could set our time between coats to 1.5, 0.5, or 1 minutes, and then the time tumbled between 1 minute, 1.5 minutes, and 2 minutes. And then the table on the right is like the results of our experiments. So in between these 2 steps, we had to just make up our own data for the results of these experiments, because obviously we can't actually run these experiments at the M&M facility. So we just had to make up our own results. And our 2 responses were total output and number of defects. So once you run the experiment all the way through, the final results are that we should use supplier 2 for chocolate. For the peanut supplier, we should use also supplier 2. We should set the time between coats to 0.5 minutes and the time tumbled to 1 minute. And that will give us a maximum output of 113 total M&Ms with a minimum of 11 defects.
So based on our analysis, we found that there's a really high number of defects per bag, and that there's a high variation of defects per bag. And we also found that the stamped M was definitely the most common defect found. Therefore, if we actually wanted to try to improve the process of M&M making, we should focus on that part.
We also found that 3 girls plus 4 pounds of M&Ms equals a lot of fun plus a bad idea.